All right, in this video, we are going to start talking about decompositions of graphs and Hamilton cycles. All right, so first off, a decomposition of a graph G is a set of subgraphs of G, and I'll just call those H1, H2 through H sub k, such that the edge set of H sub I intersected with the edge set of H sub j is the empty set. And that is for all I and j such that I is not equal to j, right, where the values of I and j are between 1 and k inclusive. So all this is saying is that these subgraphs have no edge in common. So they don't share any edges. So H1 and H2, right, don't have any edges in common. H1 and H sub k are the rest of any of the rest of the graphs in there. They have no edges in common. All right, and the second condition is that if I union up all of the edge sets of the subgraphs, right, take all of the edges and union those edge sets up, it is equal to the edge set of G. Okay, so this is what's called a partition, basically, right, of the edges of G. So the edges of G are partitioned right into these edge sets, the edge sets of these subgraphs. And so that's what a decomposition of a graph is. One thing to notice about this is that the subgraphs that make up the decomposition may have vertices in common. That's okay. So down here in this figure, I have a complete graph on 5 vertices, and I have it partitioned into 2 subgraphs. The subgraphs with the red edges in here, and then the subgraph with the black edges. So that would be a partition of this graph into 2 subgraphs. Okay, you can see that every edge of the entire graph is accounted for. They're either painted red or painted black. And there's no edges in common between those two. Okay, so here I just colored the edges to show the subgraphs a little easier. Don't confuse that with the edge colorings that we did before. Right, this is definitely not a proper edge coloring of this graph. So it's unrelated. I just colored the edges to make this a little bit easier to look at and to tell where the subgraphs are. All right. Next definition that we want to take a look at is a Hamilton cycle. A Hamilton cycle in a graph G is a cycle that contains every vertex of G. All right, so you can see that this red cycle around the edge is a Hamilton cycle, right? If I look at it, it contains every every vertex, right, of the graph. In this case, the complete graph on 5 vertices. Likewise, you can see here, right, if I take a look at the edges that are colored black and just sort of follow them around, like so, then that also is another Hamilton cycle as well. Okay, and so this graph, the complete graph on 5 vertices here, what we've done is these subgraphs that we talked about in the previous slide about that form a decomposition, they are actually a decomposition of this into, of case of 5, into 2 Hamilton cycles. Okay. All right, and so that's an interesting problem in and of itself. So notice one thing too about the Hamilton cycle is that the Hamilton cycle is going to be the largest, right, cycle that you can get in the graph itself. Okay, if it has one. Okay. All right. Because it visits all the vertices, and once you've visited all the vertices, well then there's no way that you can make that larger, right? Because to make it any larger, you'd have to go to another vertex, but you've already been to all of those, right? And so therefore you can't make a larger cycle in there. Okay, and so this theorem Theorem 2.3.1 in our book is proven by Lucas, who attributed this decomposition to Wallecki. And that is that the complete graph K sub 2 sub n plus 1 has a decomposition into n Hamilton cycles. So first, right, note that this K 2 sub 2 times n plus 1, that is an odd number, right, because it's one more than an even number, right, a multiple of 2. So in the previous slide, we had a decomposition of K5, right? So for K5, the n would be 2. And so there is our decomposition into the 2 Hamilton cycles here. All right, here is a little bit more complicated one. This is the complete graph on 9 vertices. So for 9 vertices, our n would be 4, right? 2 times 4 plus 1 is 9. So this shows the decomposition into 4 Hamilton cycles. One with edges colored black, one with edges colored blue, one with edges colored red, and one with edges colored green. All right, and if you look through these, you can kind of notice how it goes. Let's start with the green one. That's somehow the easiest one for me to see at this moment. So starting here, you can see that the Hamilton cycle just kind of zigzags its way right through the complete graph from one side to the other. All right, until it gets kind of here to the top, right, and then you can see it connects back like this as well. If you take a look at, say, the blue one right here, you can see it starts to do that same thing as well. And they all kind of have this, that in common. And then they'll go back to where they started from like that. So if you look at the red one, it kind of does that as well. So we are not going to prove this theorem. The best proof that I found for it is still just a little bit more than I want to go into in this class, because it takes a little abstract algebra, and I don't feel like everybody in this class has had that class yet, or they might be in the middle of taking it. So. All right, so but we will talk about how this, one way to look at it and sort of where the cycles come from. And this is outlined in our book as well. So I don't really consider what our book has a proof, but it's still a decent illustration of how you would think about this. So, so here we're going to go with 9 vertices, okay? And we're going to label them from 0 to 7. So that's 8, and then leave one outside here called X. And this X one is kind of special. All right, and then we're going to start putting the cycles in here. So the first one, we are going to start here at 4 and kind of zigzag our way up to the top. All right, and that's going to look like this. So we start at 4, and actually I zigged the wrong way in the previous one, although I don't think it really matters. But so we kind of zigzag our way up to the top like this until we get to that 0 there. And you can see that those edges, the way we have this drawn, we drew this in a very specific way, right? So that these were the corners, say, of a polygon. You can see that these edges are parallel to each other. So now, you know, if your proof kind of depends on that, then I think you need to formalize that a little bit better than we have here. But you can see that these edges are parallel in the way we've got it drawn, right? In reality, when you're talking about graphs, and you know, parallel doesn't mean anything, at least in the context that we've been talking about it. So, and then so you kind of zigzag your way up through the vertices here till you get to the top from one side to the other. And then what you do is you connect the top one to this outside vertex, and then connect that back into the one on the bottom through this edge X right here. All right, and so you can see that's a Hamilton cycle. It hits every single one of the vertices. If you go back and look at the finished version of it, you can see that's basically here, On the black edges, it zigzags its way up from the bottom all the way to the top. And then the outside one would be here, and then it comes back down here like this. So that's what we're looking at. All right, the next thing that we are going to do then is to rotate these vertices. So we're going to rotate everything. And 0 is going to slide down here. 1 is going to slide up to the top. So all these numbers are going to kind of change position. So you can see the 0 moved down here, right? 7 moved from here down here. So we rotated everything a little bit. And then we are going to do the same thing. We're going to start at the bottom, zigzag our way up to the top. And this time we did it in blue. So when we get to the top, then we connect to that outside vertex and then go back down. All right, so that is another Hamilton cycle. You can see that none of the edges are shared, right, between the black and the blue ones. All right, and then we're just going to keep playing that same game again. So we're going to rotate. Now 1 will be down here, 2 will come up to the top, 6 will come down to the bottom. All right, and then we'll connect that up, and this time I colored the edges red to distinguish this cycle so you can see it more easily, right? So it'll stand out from the blue and the black ones. And once we get to the top, we connect to this outside vertex and back down. So you can see again, that is another Hamilton cycle. It visits all of the vertices, and you can see there's no edge in common, right, between there. And remember, we are talking about the complete graph, right, and so every vertex is connected to every other vertex, right? And so we're slowly filling up all of the vertices in here. All of the edges. We're slowly adding the edges each time to there. And then we'll stop when we have all of them in there. All right, so rotate this again. And then play the same game, right? Start at the bottom, this time at 7. Work your way up diagonally like that until you get to the top. Connect to the outside vertex, and then connect that vertex to 7 there. And we've got another Hamilton cycle. And at that point, we can stop, right? We have now every vertex, if you look, right, is adjacent to every other vertex in the graph. And so here we've got a decomposition of K9, right, the complete graph on 9 vertices into 4 Hamilton cycles in this case. Okay? So that's how you do it for K9. Here is a list of the cycles. You can see that first one that we started with was 0.7162534x, right? So that was this one, right? 0.7162534x. All right, and another interesting thing here is that you can get the next one, the next cycle, the vertices in there by adding 1, and then modding out by 8 in this case. Okay, so 0 plus 1 is 1, 7 plus 1 is 8, mod 8 would be 0. 1 plus 1 is 2, 6 plus 1 is 7, 2 plus 1 is 3, 5 plus 1 is 6, and so on and so forth. So that gives you the vertices here. And of course this x, the outside one, stays the same. Then to get the third vertex, and you can just verify that if you look back at the blue ones, right? 1, 0, 2, 7, 3, 6, 4, 5, and connect to the outside. And the same thing, you can keep going. Add 1 to each of these. 1 plus 1 is 2, 0 plus 1 is 1, 2 plus 3 is 1. 7 plus 1 is 8, mod 8 would be 0, right? And so on and so forth. That gives you the third cycle, and this gives you the fourth cycle as well. All right, so that's what our cycles look like. And in general, right, they would kind of look like this. This is the general plan. You can see that on each one of these, right, you can see it goes 0, 1, 2, all the way up to n minus 1. And then n here right before the x. And then going backwards, it would kind of go up. So if we go back and look at that pattern, right, we have 0, 1, 2, 3, 4, 5, 6, 7. So that's how that first one would go. And then likewise, we can get the next one by adding 1 and then modding out. In this case, it would be 2n minus, or let's see, it would be, we're doing 2n plus 1. So that would be modding out 2n. Right? So here I add 1, 0 plus 1 is 1, 2n minus 1 plus 1 would be 2n mod 2n, that would be 0, right? Because 2n goes into 2n evenly, right? And so it follows that same pattern. That will give you your n cycles there, n Hamilton cycles, I should say. Okay. All right. So again, I don't really consider that a proof. We would need to hash out a bunch of details there. And honestly, doing it that way is kind of awkward. I did find what I thought was a really nice proof, but again, it's kind of at a level that I didn't want to go into. We'd have to talk about permutations and groups and things like that. So, all right, and so that's it for this video, and we will put the rest of the theorems in their own video.